So now let's prove another property. We claim that the absolute value of the integral of f is bounded by the integral of the absolute value of f. And well, this is very easy. So we know that f it's an integrable function. So f d mu it's the integral of the positive part minus the integral of the negative part. So if I take the absolute value of this quantity, this is the absolute value of that quantity. These two numbers are non-negative, so their absolute value it's bounded by the sum of these two values. Now, by linearity of the integral, this is equal to the sum, the integral of the sum. And the sum of the positive part with the negative part is just the absolute value, and therefore we have indeed that the absolute value of the integral of f it's bounded by the integral of the absolute value of f. So this is a simple property. So now another property, the fifth. So if I take c a real number, what I claim is that c times the function f it's an integrable function, and that the integral of c times f it's equal to c times the integral of f. So let's first see that c times f it's integrable. Well, c times f it's clearly equal to the integral of c times the absolute value of c times the absolute value of f. Now, therefore, the integral with respect to d mu of this function it's equal to the integral of that function. And we have already proved that if we have non-negative functions and non-negative real numbers, that the integral it's linear for that. So this is equal to c times the integral of, so the absolute value of c times the integral of the absolute value of f. F it's integrable, therefore this integral is finite. C is a real number, so this is finite, which therefore shows that the integral of the absolute value of c times f it's finite, and therefore that the function c times f it's an integrable function, right? Because to show that a function is integrable, we need to show that the positive parts and the negative parts are integrable, but both the positive and the negative part are bounded by the absolute value. So both the positive and the negative part of the function c times f are integrable, and therefore c times f it's an integrable function. So now let's prove this identity. So for this identity we'll consider all possible cases. So let's start with c equal to 0. Well, if c equal to 0, then c times f it's 0. The integral of 0 it's equal to 0. F it's an integrable function, so this integral it's a real number, times 0 it's equal to 0, and we have on both sides 0, so that the identity is in force. So for c equal to 0 it's very easy. Now let's take a positive number, the real number c. So by definition, c f d mu it's equal to the integral of the positive part minus the integral of the negative part. Right? So this is just the definition of the integral of an integrable function. Now, since c it's positive, the positive part of c times f it's equal to c times the positive part. And for similar reasons, the negative part of c times f, it's c times the negative part of f. So we have this identity. Now, c, it's a positive real number, f plus, it's a non-negative function, same thing here, and we have seen that in case of non-negative functions and non-negative real number, the integral is linear. So these are equal to c times f plus minus c times the integral of f minus. I don't write d mu. So this is equal to c times the integral of f plus minus the integral of f minus, and this is just equal to c times the integral of f. Right? So here's the proof of the linearity in the case in which c is non-negative. And for c positive. For c negative, the proof is very similar. So let me just erase this. So now let's assume that c is negative. So I start with the same identity. C times f, by definition, the integral of c times f, it's equal to the integral of the positive part minus the integral of the negative part. But now c, it's negative. So if I want to take the positive part of c times f, I have to take the negative part of f and multiply that by minus c. Right, so what I claim here, and I leave it to you to check, is that the positive part of c times f, when c is negative, this is the negative part of f times minus c. In the same way, if I take the negative part of c times f, what I have is that this is the positive part of f times minus c. And now again I can repeat the same argument I used for c positive. Since c is negative, minus c is positive. F minus is positive, so by linearity this integral is equal to minus c times the integral of the negative part of f. And in the same way, since c is negative, minus c is positive, f plus the positive part is positive, so by linearity this is minus c times f plus the mu. So now I have minus with minus plus, so I have c times f plus minus c times the integral of f minus, so this is c times the integral of f plus minus the integral of f minus, and this is c times the integral of f. So again, if c is negative, the integral of c times f d mu is equal to c times the integral of f d mu. So we just proved this claim. So now I want to prove that the integral is monotone, in the sense that if I take a non-negative function f, then its integral is non-negative. And in the same way, if I take two functions f and g such that f is larger or equal than g, then I obtain that the integral of f is larger or equal than the integral of g. So let's start with the first one. Well, by definition, the integral of f it's equal to the integral of the positive part of f minus the integral of the negative part of f. But f is non-negative, so the integral of the negative part of f is equal to 0. So this is equal to the integral of the positive part. And this object now is defined as the limit of integrals of simple non-negative functions, which is always non-negative. So we do have here that indeed the integral of f d mu is larger or equal to 0. In fact, what I'm showing here is that we may have two different definitions for the integral of a non-negative function. Right? We started defining the integral of a non-negative function as the limit of monotone sequence of simple functions converging to f. But I can also consider, and then we define that for an integrable function f, let me call it f tilde, we define the integral as the integral of the positive part minus the integral of the negative part. Right? So you see that if you have a non-negative function, you could adopt two different definitions, either consider this definition or consider that definition. And what I'm showing here is that they in fact coincide. So if you adopt any of these two definitions as the integral of a non-negative function as the difference of these two integrals, well, this one will be 0, so that one is equal to that one, and that one is given by the limits, so these two definitions coincide. And in particular, if you have a non-negative function, the integral of this function, it's always non-negative. So this is the proof of the first assertion. And let me go now to the proof of the second one. Well, let's assume that f is greater or equal to g. So from that, I get that f minus g is greater or equal to 0. From the first piece, we know that f minus g d mu it's greater or equal than 0. And now by linearity, this integral is equal to the integral of f d mu minus g d mu. F and g are integrable, so these are real numbers, and these real numbers are greater or equal to 0, which means that the integral of f is larger or equal than the integral of g, which is what we wanted to prove. So here is an interesting property. Take a non-negative function and assume that its integral is equal to 0. Then we will show that f is equal to 0 almost everywhere. So for that, let me call En this set of points such that, so these are the x in omega, such that f of x it's larger or equal, say, to 1 over n. And, well, the indicator of En times f, it's certainly less or equal than f, and therefore, by the monotonicity of the integrals, these are non-negative functions, and therefore this one is integrable because f is integrable. So if I take the integrals on both sides, by monotonicity I get this inequality. But on the other hand, on the set En, fx it's greater or equal than 1 over n. So what I have is that the function indicator of En times f, since on this set En, f it's larger or equal than 1 over n, this function is certainly larger or equal than 1 over n times the indicator of the set En. So again, I can use the monotonicity of the integral to say that the integral of this function is larger or equal than the integral of that function. So this is what I'm using here. I have here the integral of 1 En, 1 over n, d mu. But now, on the left-hand side, what I have is a simple function. A function which is equal to 1 over n on the set En. And therefore, I get that 1 over n times mu of En, which is the integral of this simple function. This is less or equal than the integral of f, but the integral of f is equal to 0. So, and of course, this quantity here, it's non-negative, and therefore, this means that the measure of the set En it's equal to 0. Right? By assumption, the integral of f d mu is equal to 0. I obtain this identity, the sequence of inequalities, and therefore that the measure of En divided by n is less than or equal to 0, therefore that the measure of En is equal to 0. Right? Well, if the measure of En is equal to 0, let me call E the set, the union of these sets. By subadditivity, mu of E is less or equal than the sum of mu of En, and since each one is equal to 0, this set has measure 0. Therefore, mu of E is a set of measure 0. Well, but on the set, so let me erase, so let me just recall that En is this set, E is the union, and that the measure of E is equal to 0. So let me erase the sequence of inequalities, which I will not use anymore. So what is this set En? The union, what I claim is that E, it's exactly the set of points such that f of x it's strictly larger than 0, right? Well, so I claim that these two sets are equal. E, it's by definition this set, right? So let me write maybe as the union of En. What I claim is that the union of En, which I called E, is given by this set. So let's first prove that this set is contained in that one. So let's take a point in this set. This means that f of x is strictly larger than 0. If it's strictly larger than 0, it should be larger than 1 over n for some n, and therefore this point is contained on one of the En's, and therefore in the union. So this set is contained, the right-hand side is contained on the left-hand side. So now let's prove the reversed inclusion. So we have to show that each set En is contained in that set, but take a point in the set En. This point is such that fx is larger than 1 over n, so it's certainly larger than 0, and therefore each En is contained on that set, and therefore the union is contained in that set, and this proves the identity. So E, I call this set. So I just proved that the set E, it's in fact the set of points x, such that f of x is strictly bigger than 0, and we proved that this set has measure 0. So we proved that f is equal to 0 almost everywhere, right? Because we proved that the complement of, so that the set f, we just proved that the set f bigger than 0 has measure equal to 0, right? So we proved that this set, which is E, it's equal to, has measure 0, and therefore since f is larger or equal to 0, this means that well, the complement of this set it's has full measure, so that f it's indeed equal to 0 almost everywhere. So now let's prove that if I have two integrable functions which are equal almost everywhere, then their integral are equal. Well, that's very easy. Let's call E the set in which f is equal to g. So this is certainly a set in the sigma algebra because f and g are by assumption measurable. And since they are equal, this means also that the complement of E has measure 0. Okay? Because f and g is equal to, f is equal to g almost everywhere, this means that the measure of the complement of this set is equal to 0. Now I can write f, the integral of f, as, well, I will decompose the set omega in two sets, the set E and the set E complement. So this sum, it's of course equal to the sum of the indicator of E times F plus the indicator of E complement times F. Right? Here I'm just writing 1 as, so observe that this is equal to 1, right? So I'm writing 1 times F as the sum times F. And now I'm just rewriting this product as this sum. I will use here the linearity of the integral, which we proved, to say that this is equal to plus but on the set E, F is equal to G. So I can replace here F by G. On the other hand, since E complement has measure 0, we have seen that the integral of any function on a set which has measure 0 is equal to 0. So this integral here, it's equal to 0. So up to this point, we proved that the integral of f d mu it's equal to the integral of g multiplied by the indicator of the set E d mu. So now, again, since E complement it's equal to the measure of E complement it's equal to 0, I can rewrite this integral as the same integral plus the integral of the indicator of E times g d mu. And once I reach this point, I can just go back in the argument to reach that this sum it's in fact equal to the integral of g d mu, which is exactly the statement we wanted to prove. So we have just seen that if I have two functions which are equal almost everywhere, then their integral coincide. So now let's prove the following property. Consider a function h defined on omega and taking value in the extended line. Assume that h is measurable and that the absolute value of h is bounded by a function which is integrable. So non-negative function which is integrable. Then what I claim is that h is integrable. Well, to prove that h is integrable, we have to obtain a bound of the non-negative part of h. We have to show that this is finite, and the same estimate for h minus. Right? To show that the function h is integrable, we have to prove that the integral of the positive part and the integral of the negative part are both finite. Well, but h, the absolute value of h, is bounded by f. So by monotonicity, we know that the positive part of h is bounded by the absolute value of h, which is bounded by f. So we know that the positive part of h is bounded by f. And therefore, by monotonicity, the integral of h plus is bounded by the integral of f. And f is integrable, so this expression is finite. And therefore, we have proved that the integral of the positive part of h is finite. And we can repeat the same argument to the negative part of h, showing that these two integrals are finite and therefore that h is integrable as we claimed. So now let me just conclude this sequence of properties of the integral with an estimate. Assume that you have a function f, and which is well defined on some measurable space omega f mu, and suppose that there exists, so f, it's a measurable function, and that there is a set f, that there is a set E, such that f is bounded by C on a set E, and the E has finite measure. And while f it's equal to 0 on E complement, then I claim that f is integrable. So it's a result which allows you to show that some measurable function is integrable if it's bounded on a set of finite measure and equal to 0 on its complement. And the proof of this result is very simple. Well, to show that f is integrable, we have to bound the integral of the positive part and the integral of the negative part. But in order to bound that, since the negative part and the positive part are both bounded by the absolute value, it's enough to show that the absolute value of the function is integrable. Now we have this set E, so let me decompose this integral in two pieces, one in E and the other one on E complement. So by linearity, this is equal to f on E plus f on E complement. Where we use linearity. Now, on the set E, f is bounded by C. So this function here, it's bounded by C times the indicator of E. So by monotonicity, this is bounded by C times the indicator of E integrated with respect to mu. And on the other hand, f it's equal to 0 on this set. So we have here a function which is equal to 0, and therefore its integral is 0. Now this is a simple function, and therefore its integral is equal to C times mu of u, which is finite because, well, E by assumption is a set of finite measure. So we just seen that the absolute value of f it's integrable, and therefore the function f is integrable as we claim.